Welcome to 60-second lecture on electrical machines 1, and we are discussing about DC machines. And in DC machines, the armature winding is slightly difficult, unlike AC machines windings. But although the basic features of a winding is still present, that is, each coil will be generally full pitched coil, and they will have two coil sides, and the separation between these two coil sides will be 180-degree electrical. So, in this simplified diagram, you recall that earlier we for a 4-pole machine, we had this simplified winding diagram. I need not go to slot and show the exact winding, how it is done, provided I know how I am representing a coil in these slots in this diagram. That is, suppose 7th coil S7 and its finish is another coil side F7. And if at any point of time this coil side S7 is under north pole, F7 has to be under south pole. And after assuming some direction of rotation, generated voltages were shown, and then we found that no matter which coils occupy this particular position, which is presently occupied by 7th coil, whether it is 6, 5, whoever comes here, because these things are rotating, they cannot but have this polarity of induced voltage, and whose magnitude will be also same. This prompted us to think that okay, in that case I will take from the junctions with the help of conducting wires, terminate on some commutator segment circular, and then I will place fixed brushes in space, which will be stationary, but in which position, where plus plus will be joined, where minus minus will be joined, negative brush here, plus plus joint, positive plus, and this one. We explained this. So, there will be, in case of this lap winding, there will be 4 brushes, B1 and B4, they can be joined together, and 4 brushes will have to be connected. Okay. Then this is not how exactly this is done. Last day I forgot to bring this model. So, this portion, that is this and this copper strips, these are done by what is known as commutator segment. If you look at it very carefully, in the commutator segments, there are several commutator segments, and which is mounted on the shaft, and 2 commutator segments, this and this next commutator, they are insulated by, it is looking like a gap, but there is a mica insulation. Okay? So, that each commutator segment has got its own identity. Therefore, commutator segments, number of commutator segments will be just replica of the number of slots here, if they are equal in numbers. We will consider the simplest case, when the number of commutator segments are equal to this one, because in each commutator segment 2 ends of 2 different coils will be joined. Therefore, number of commutator segments has to be equal to number of slots present in the machine. So, this whole thing will rotate. Okay. And then we will have carbon brushes. Suppose this tip is a carbon brush placed in space like this and fixed. Therefore, as it rotates, this fellow does not rotate, this one, this brush, it will touch whichever coil comes in that position, it will connect that particular commutator segment. ensuring that B 1 and B 4 will remain always positive, B 3 and B 2 will always remain negative polarity of the voltage, thereby giving you a DC voltage. And another thing you note that, so these two terminals, so commutator segment later I showed that it can be like this. If you go, there will be commutator segments here, and each coil, suppose S 1 and F 1 is a coil, its two ends will be terminated here and it will be terminated there. The commutator segments where the coil ends will be terminated of a particular coil, the difference this length is called commutator pitch. Commutator pitch. Which is denoted by YC. In case of lap winding, it will be equal to plus minus 1, okay, plus 1. So this coil number 1 is connected to adjacent commutator segment. Similarly, coil number 2 will be actually connected between 2 and 3. Okay. So from 2 you start these junctions and your 2 and this side it will be terminated on 3. Like this. Then S 3, it will continue like this. So, this is called commutator pitch. This is what the difference between the commutator segment numbers of a particular coil, which happens to be plus 1 in case of lap winding. Okay. So, and after we complete it, then we make the winding table as I have shown, simplified winding table, and from here I know at which junctions the brushes are to be placed. Everything is known, B 1, B 2, B 3, B 4 if it is a 4 pole lap winding, which two are plus, which two are minus. Brushes are stationaries, I will connect them and ultimately get the armature terminal. Okay. Now, and this one can complete, I leave it as an exercise up to 16 coils you complete, then put plus minus here, they are also, and the commutator segment, first coil 1 5 dashed in terms of slot number 1 2 2 3 like that, and then you can determine the position of the brushes much more scientifically. If time permits, I will further discuss on this, but it is not necessary at this stage. Therefore, I now know that field winding, a DC machine, I will represent it schematic diagram. I will show the field winding like this, F 1, F 2, and we know how these two terminals are coming, and armature I will show it like this, a circle and two brushes. Even if it is a 4 pole machine, only 2 brushes I will show. Why? Because of the reason that it is the equivalent simplified representation. Okay? Whatever is happening under a pair of pole in the armature conductor, under the next pair of poles, same thing is bound to happen, is not? North south, whatever is happening, whoever conductor is present, under the next pair of poles, same thing is going to happen. Therefore, it is the simplified representation which are called the armature terminals. A1, A2, which are coming from where? If it is a 4 pole machine, B1, B4 you have shorted, got this, and B2, B3 you have shorted, you have got this. Now, if you look carefully between this diagram I will refer to, previous to this is a 2 pole machine. If you join like that, you can easily see, if you start from B1, you traverse 4 coils and you come to minus. Okay. So, between positive and negative brass, this is one parallel path. It could be, you could reach the negative terminal, because negatives are shorted also. So, B1 another 4 coils and you reach the negative terminals. So, second parallel path. Okay. So, here is one parallel path, here is another parallel path. Similarly, from this positive terminal, if you want to reach the negative, you see 4 coils, you reach the negative. From this another 4 coils, you reach the negative. Therefore, between the positive and negative brushes, the armature circuit, all the coils will be divided into as many parallel paths as the number of poles of the machine, provided it is a lap winding at least, because I have not discussed anything about wave winding, that I will do slightly later. So, for lap winding, the conclusion is, between the brushes there will be a number of parallel paths. A number of parallel paths means, if the number of poles of the machine is 4, number of parallel paths between positive and negative brush will be 4. If it is a 6 pole DC machine, number of parallel paths will be 6. So, this point you please see, it can be easily seen from plus to minus if I want to reach, because it is this plus plus thing what I am telling. I will write here A1, A1 I have written, yeah, I have written, sorry. This is the brush A1 plus, this is A2. So, coming back to now the simplified diagram, this A1 is coming from the junctions of B1 and B4, which are positive, and this is suppose positive, and these are called armature terminals, and this is minus. Of course, this plus minus may interchange depending upon direction of rotations, depending upon the direction of flux from left to right. But anyway, so it is if it is an idle machine, no point in showing this plus minus, but only a pair of brushes. This is how it will be shown. But what I am telling, if suppose at any time the armature carries some current here, suppose it is carrying some current here, suppose it is generator mode, it is delivering a current you have connected to the load, because it will become a sheet of EMF. We will soon find out what will be the expression of that EMF. But the point is, if it delivers current, what will be the current in the conductors flowing? It will not be equal to IA. Why? Because there are 4 parallel paths if it is a 4 pole machine. So, this current divided by the number of parallel paths, all parallel paths are identical. So, current will be equally distributed in the parallel paths. So, if number of parallel paths, if I say, if IA is the external armature current, then current through the armature conductors, through the armature coil sides or conductors, armature conductors will be equal to I A, the external armature current, divided by A, where A is the number of parallel paths, in the armature circuit, that is across the brushes. Mind you, it is important to note this external current and the armature conductor currents, they are not the same. In case of lap winding, we have seen, in case of lap winding, A, number of parallel paths, A is equal to P, equal to number of poles. Of the machine. Is that clear? So, this comes naturally. If it is a two polar machine, lap winding, number of parallel paths will be 2. It can be easily seen, because we have seen that. Two pole winding, we have drawn the physical that winding diagram, two pole machine. You see, there are only two brushes, B1 and B2. To reach from plus brush to minus brush, you traverse either this way 8 coils, reach minus, and another alternative path is this one, 2 parallel paths for a two pole machine. Hopefully, you have understood this. Okay. Now, today I will do one very important thing, that is, suppose I will say I have a DC machine with a field winding and armature winding. I will run the DC machine by a prime mover at certain RPM or RPS. I know will be knowing the field current, which will create a flux along this line, and I would like to know what will be the EMF available across the brushes of the machine, across the armature terminals. On what factors it will depend and how to calculate that. So, let us try to do that first. So, consider a DC machine. It is the armature terminal. Calculations are simple in case of DC machine. This is the field winding and this is the phi called the flux per pole. If you have passed a current IF, north south will be created, the other side is generally not shown. So, flux is created and this is often called D axis, forget about this name right now, it is not necessary. So, this is the flux. Incidentally, if you look at it, why brushes are shown here, not here, also will be apparent from this diagram. Okay? Brushes will be always along the quadrature axis, clear. So that is why the brushes are shown like this. Okay. Now, I have a flux per pole created, and suppose I decide I will run the machine in a particular direction with a speed of n RPS, rotation per second. If it is RPM, divide by 60 to get this number, and it is across the armature terminal. I want to calculate how it is driven. It is driven by a prime mover, because generator, as a generator I want to run it, maybe a diesel engine, maybe a steam turbine, whatever it is. So, prime mover drives it at n RPS. Then the question is, what will be the generated voltage, that is reading of the voltmeter when no load is connected. That is our intention is. Okay. First is how to calculate flux. IF is known, therefore, and IF is DC. Okay. So, this MMF divided by reluctance of the path will give you some flux per pole. Okay. Now, if flux per pole is known, but I want to calculate the generated EMF, I told you that flux density distribution will be somewhat trapezoidal, is not? That is what I told. Okay, this is 0, this is space angle theta, this is pi, this is 2 pi, and lines of force entering into the stator is suppose south pole, anyway B distribution, under which, and this field pattern need not be sinusoidal, because here my intention is not to get a very nice sine wave voltage. Whatever will be the nature of this B, that will be the nature of the induced voltage in the coil sides or in the coil, because two opposite coils are under two coil sides are under different poles, their direction of rotations are same. Therefore, these two voltages will be additive, we know that 2B LV will be the voltage across the coil, and the value of B, whichever conductor will be here, suppose, and this fellow is stationary, it is not moving at all. So, armature conductors, if I show it like this with red lines, armature conductors are here in these slots. Is not? And armature is moving, suppose from left to right. And this field is stationary, and suppose this is south pole corresponds to, this is north pole. Then I will apply right hand voltage to find out the voltage induced in a single conductor. How to do it? This is the direction of, say, tangential velocity V of this conductor, say. I want to find out what is the voltage. This is B, this is B, this is V, direction of voltage, and this forefinger, this tip will tell you the polarity of the induced voltage coming. In fact, for all the conductors, this will be dot dot like that. For all the conductors this is true, they are having same velocity. However, the magnitude of the voltage induced in this coil will be, I have to take this B, length of the conductor is same perpendicular to the paper, into V. The induced voltage in this conductor will be this B, length and velocity is same, but nonetheless polarity is same, that is what I am telling. So, and similarly you can easily see it will be cross here, the polarity of the induced voltage, they will be additive. What I will do is this, I will start from this, that induced voltage in a single coil, I will use a better pen. I will first calculate induced in a single conductor is how much? You pick up a single conductor, what is the induced voltage in it? Now, it may look a bit funny that this conductor will traverse this whole length as time passes. Okay, polarity remains same, but the magnitude of the induced voltage here, because this fellow was a little time, a time earlier was here, it has now occupied this position, induced voltage has become more, B is more. Then once again it retains that value if it is flat top, then once again it is decreasing. Therefore, magnitude of the induced voltage induced in a single conductor is not constant when it is under one pole, that is fine, but its polarity remains same. So, what people do is this, okay, this conductor is seeing different value of flux density between 0 to pi. So, why not take the average value of the flux density and multiply with L and V to get that voltage, that will be absolutely accurate, nothing wrong in that. So, what you do, you take average value of this B, which will be something here, B average, total flux. What is B d theta? Total flux divided by this length, average value of flux density I will calculate and pretend that the conductor sees all the time B average and multiply with that B average with length and velocity. Now, the big question is how to calculate B average. That calculation is also very simple. See, if you look at this diagram, suppose it is a multipolar machine, I will draw it here, say 4-pole machine, this is suppose north pole, this is the south pole, this is once again north pole. Windings I am not showing on the stator, we know how to create that. This is suppose south pole. Suppose air gap is little, so suppose the diameter of the rotor or the air gap, whatever you call it, it is suppose d, diameter of rotor is equal to d. This north pole will create flux which will come out as we have seen, it will go like this, is it? That is how it will be completing through this other portion of my irons, EOX that is called. Anyway, So, B will be present here, 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 here. Then there will be a, if you draw a line, dotted line I am showing, these portions there will be no flux density perpendicular to the iron, because there is, it is 0, nothing. So, whatever total flux comes out from the north pole, which I have denoted by phi, phi is the let phi is equal to total flux per pole, total flux per pole in Weber, suppose. So, this flux, what will be this length? If d is the diameter of the coil, I mean not that length, this length on the periphery, this length, how much will be this length? Because B I have to calculate, I have to divide the total flux per pole divided by area. So, I must know what is the length of this one, this portion. I highlight it with different color. Got the point? Here, this length is how much? This length will be, obviously, this length is pi d, is the total periphery, divided by number of poles. If it is 4 pole, pi d by 4, 4 pole I have shown. If it is 6, pi d by 6. So, flux per pole, and what is its unit? Its unit is in meter, and area through which this phi is acting, I mean is present, whatever language you write, will be equal to pi d by p into length of the machine, because this is perpendicular, is not? That will be the area. Curved area, we assume, okay, this is sort of rectangle, pi d by p into length of the machine, that will be the area. Therefore, B average in the air gap, I can say flux per pole divided by the area through which this flux per pole, this is phi, total flux, all the lines of force coming out, phi, distributed over this length pi d by p into L. So, this is pi d by p into L, which will be equal to phi p by pi d L. What is d? Diameter of the rotor. What is L? Length of the machine or the length of the conductor, because rotor length is the coil side length, you should remember. These are overhang portions. In these portions there will be no induced voltage, I should not bother. I will be bothering about the effective length of the machine. Here the voltage will be induced, this fellow is rotating, seeing different values of flux density under a pole. Although polarity of the voltage remains same when it is under south pole, but magnitude may change because strength of B is changing. That is why it will see sometimes low value of B, sometimes higher values of B, once again back to low value. Therefore, why not calculate the B average and pretend that B average remains constant, multiply with L and V, and you will get absolutely correct result, nothing wrong in that. So, induced voltage, this question mark, I can now write it as is equal to it will be in a single conductor, mind you, in a single conductor will be B average, B length of the conductor, and V the velocity. And I can if n is the RPS, this mind you is the linear velocity meter per second. So, if it is n, then conductors residing here and the rotor diameter is n, then velocity in meter per second is nothing but pi d n. In 1 second conductor will travel how much distance? Pi d is the perimeter. In one rotation pi d, in 1 second it makes n rotation. So, in 1 second it will move by so much meter per second, is not, and that is the thing. So, I will say that induced voltage, let it be a bit clumsy, I do not mind, but let me on this page only. So, it will be then is equal to B average L, and for V I will write pi d n. This is the expression for induced voltage in a single conductor. We will continue with this in the next lecture. Thank you.